So, this leads us to the Nyquist theorem, and what the Nyquist theorem says is that if your Nyquist plot of G open loop, if your Nyquist plot of G open loop does not encircle -1 0, this is the real axis, this is the imaginary axis on the G plane, this is the G plane, does not encircle -1 0, then the closed loop single input single output feedback system is stable. On the other hand, if it encircles -1 0, so this one is stable and this one is unstable because it is encircling -1 0, and of course, if you got one that goes like this, passes through, this one corresponds to sustained oscillations. So, the Nyquist theorem says if the Nyquist plot, if Nyquist plot of G open loop, the feedback loop is not yet closed, does not encircle -1 0, then the closed loop single input single output system is stable. Of course, the opposite is also true. So, it is a necessary and sufficient kind of concept, else unstable. And of course, there is an assumption there that the open loop system by itself is stable, you do not have a open loop unstable system, all right. Okay. So, this is the Nyquist theorem, and now this sounds like magic. You look at G open loop j omega, make its Nyquist plot, and if the open loop Nyquist plot does not encircle -1 0, closed loop system is stable. So, this sounds like magic, but where does this magic come from? I will quickly go through that, and it comes from complex, basically a bit of complex analysis. So, let us say I have got G is a transfer function which is product of what? The zeros over I and product of poles over plus, should I make it plus or minus? I do not know. Well, let us just do it. Let us say this is G. Okay. Let us say if we talked about the characteristic equation, and if the characteristic equation roots are in the right half plane, then you get an unstable system. For a feedback control system, the characteristic equation is 1 plus G open loop is equal to 0. So, it actually all boils down to figuring out if any of the roots of this equation are in the right half plane or not. Okay. So, I will just tell you how it works out. So, let us say this is the S plane and this is the G plane. S is a complex number and S is S is equal to sigma plus j omega. G is also a complex number which is a function of S. So, as S changes, G, which would be a complex number, would also change. All right. Now, let us say I got S which is here. For this value of S, when I substitute this value of S into this expression up there, into the expression for G, I will get another complex number, a complex number for G. Let us say I am plotting that complex number, and that complex number turns out to be somewhere here somewhere. So, this is G corresponding to this S, all right. All right. Now, let us say this S is moving in a closed contour, and let us say it is moving like this. What I do is I also plot these poles and zeros, and these poles and zeros would usually be real, but sometimes you can also have complex conjugate poles and zeros, all right. So, if I do that, so this is the real axis, this is the imaginary axis, this is the real axis, this is the imaginary axis. Now, what I do is I also show where the zeros are and the poles are, and the zeros I will show with a circle, that is a 0, and the poles I will show with a. So, this is called the pole 0 map. So, on the S plane I will also show where the pole zeros are, and let us just say that some of the zeros are outside, some of the poles are outside, but then maybe one pole is inside. Let's make a two poles are inside, and one 0 is here, and then of course there are, let us say, complex conjugate. Well, you do not really need complex conjugate also, actually it could be this is in general. Anyway, how will it be made? It will be made like this. Okay. So, let us say for the time being that we are not talking, let us say this is what things look like. Just to keep it simple, some of the poles are outside, some of the zeros are outside, and maybe let us say one pole is inside the contour. Okay. Then, so you got one 0 which is here, and you got two poles, one of the poles is here and the other pole is here. Let us say we got a system like this. Then, when S is here, let us say I have got a point S which is here, this is S, okay, the black one. Then I draw a straight line here, I also draw a straight line here, I also draw maybe a straight line here. Okay. This is the angle, then this is the angle. Okay. All right. Now, so when I look at G, G would be S minus Z1, and this S minus Z1. So, okay, this plus Z1, this, okay, so yeah, okay, so this is the vector which is S minus Z1, this is the vector which is, so we will call this P1, P2, Z1. So, maybe I should color code a few things here. So, let us say this is the Z minus P1, and let us say the purple is this is Z minus P2, red is Z minus S minus Z1, purple is S minus P2, and this let us make this green, this guy is S minus P1. So, you can see that the red curve is, this guy is S minus Z1, the green chap is S minus P1, and the magenta chap, this guy is S minus P2. All right. Then the complex number G will turn out to be, well, of course, S minus P minus Z1 divided by S minus P1 into S minus P2. Now, this guy would be a complex number with a magnitude, I will call it Z1. Let me call this complex number Z1, let me call this complex number Z2, and let me call this complex number Z3. So, then in that case G will turn out to be magnitude of Z1 times exponential of angle of Z1, and I will call the angles of zeros psi 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 1 times j, and the angle of the poles as Z2 times e to the power phi 1 of j, and the last guy would be Z3 times e to the power phi 2 of j. All right. And now, if I solve it further, what I will get is that G of S is actually equal to Z1, Z2, Z3 times e to the power psi 1 minus phi 1 minus phi 2 j. Note that the angles subtended by the zeros are positive, while the angles subtended by the poles become negative, because when you take the angle from positive angle from denominator to numerator, e to the power phi j becomes e to the power minus phi j. Okay. So, if you generalize this, what we get is that if you got so many zeros and so many poles, the angles of the zeros will get added, the angles of the poles will get subtracted. This much is clear. So, now as S is moving on the contour, as S moves on this contour in this direction, do you see that? Man, maybe I should do it on the board. So, this is the S plane, and I have S moving on a contour. I have got a pole inside, and I have got a 0 here, and maybe a pole here. So, this was P1, this was P2, and this was Z1, and what I was saying was, this is S minus Z1, and then this is psi 1, this is S minus P1, and this is phi 1, and this is S minus P2, and this guy is phi 2, and corresponding to this is the S plane. Corresponding to this, when I take G is equal to product of S minus Zi divided by product over J of S minus Pj. So, let us say this guy maps somewhere here, then what I just showed you was Gs is going to be well, let me call this number by Z. Let this complex number be called Z0 I, and let this complex number be called Z pole j. Then what I have is Gs is product of the magnitudes of all those S minus Zi terms. So, Zi divided by over I, product of j times product over j of the S minus P terms. So, Z P j, this would be the magnitude, and the angle would be e to the power summation psi I, which is the angle subtended by the S minus Zi terms, minus summation phi j. So, this is E I and this is j, then you combine it and this is actually multiplied by the square root of minus 1, which is j. All right. So, this is what we have. So, now we get the complex number g of S corresponding to a single S. Now, let us say I am going this way, I am going around the contour, I go around the contour. As I go around the contour, do you see that this angle increases, this angle psi 1 actually is, right now it is positive, then it goes negative, and then once it turns back again, and when you reach back here, then it goes this way, and then when you reach back here, the angle, total angle swept, you see this angle, the total angle swept is 0. This line actually goes like this, and then so angle is decreasing, becoming negative, then it starts to increase again, then it increases, and when you get back the angle is the same. So, the net angle swept by psi 1 as S moves around the contour is actually 0. Similarly, the angle swept by this guy, again it is a positive angle, then it goes negative, then it starts to increase again, and then when you come back to this point, it goes back to 0, or back to the same value, right. So, as S moves along this contour, the angle swept by Z1 and by these two vectors, the angle swept is actually 0. On the other hand, when you are going around the contour, the S minus P1 terms sweeps an angle of 2 pi 360 degrees. The angle as you go around here increases by 2 pi, yes or no. Okay, so, once you see this, suppose you had another pole here, let us say there was a P3 here, the angle of this guy would have also increased by 2 pi. Yeah. So, any zeros and poles which are inside the contour, so this angle sweeping would be actually, well, if you are saying that the angle anti-clockwise is positive, pole is sweeping minus 2 pi, but then when you take it up, because the pole terms are in the denominator, when you take those angles to the top, the phi's will become positive. Okay, so, poles sweep an angle of plus 2 pi, zeros sweep an angle of minus 2 pi, and these poles and zeros which are inside the contour, closed contour. Okay. So, as S moves on a closed contour, the angle of G, the net angle of G will change by 2 pi times number of poles minus number of zeros inside S contour, because poles change the angle by plus 2 pi, each pole inside the contour will change the angle by plus 2 pi, each zero inside the contour will change the angle by minus 2 pi. Yeah, inside the S contour, and S is moving clockwise. Okay. That is the kind of thing that we see from here. Now, how does this translate? How does this translate to the Nyquist theorem? That is the next thing that we will show. Okay. Now, let us talk about the Nyquist theorem. To decide if you have, this is the S plane, you got G. To decide if G is stable or unstable, you need to find out how many how many poles or okay, so 1 plus G. Okay. So, what I can do is 1 plus G open loop equal to 0 is the characteristic equation, and I want to find out whether any of the roots of this 1 plus G open loop equal to 0 are in the right half plane or not. I am assuming G open loop is well behaved, no zeros or poles with no control, that means the open loop system has no zeros or poles in the right half plane. Okay. Everything is in the left half plane when there is no control for the open loop system. Okay. So, G open loop by itself has all poles and zeros in the left half plane. That is a well behaved system, well behaved open loop system. Now, what I can do is I can plot the Nyquist plot of just G open loop and then add 1 to it. Yeah, I can make I can plot Nyquist plot of, I can make the polar plot of G open loop and add 1 to it. Now, let me take in the S plane a contour that goes like this. I may change the color, that goes like this. It is an infinite semicircle that is enclosing all of the right half plane. I want to find out whether any of the roots of this guy is in the right half plane or not. So, let it enclose all of the right half plane. Okay. All right. Then what I do is, as S is changing from 0 to, so this is actually G j omega, this is actually this guy is G with minus j omega, and what is this guy, the semicircle part, this is actually this is S equal to j omega, this would be S equal to minus j omega, and here S would be equal to a radius times e to the power j theta, theta going from plus pi by 2 to minus pi by 2. That is the contour covering the right half plane. Okay. As S is going along this curve, as S is going along this straight line, S equal to j omega, in the G plane, this is the G open loop plane. Okay. P L A N E. Okay. Real part, imaginary part. As S is going along j omega, this part, what I will get is G open loop will be nothing but G open loop S equal to j omega. So, this part is nothing but the Nyquist plot. Okay. Similarly, as Nyquist plot when S equal to j omega, omega going from 0 to infinity, that is what this is, omega going from 0 to infinity. Yeah. Similarly, when I am going along this part of the curve, S equal to minus j omega, then what I will get is G open loop, S is minus j omega. So, I am replacing j omega by minus j omega, all I will get is the complex conjugate, because I have replaced j omega by minus j omega or j by minus j. So, what I will get is the complex conjugate. Complex conjugate means the Nyquist plot gets mirror imaged about the real axis. Okay. So, when S equal to minus j omega, G would be mirror image of G minus j omega is actually mirror image of real axis or about the real axis. Okay, real axis mirror image of Nyquist plot. And then finally, when I am going around this semicircular part of infinite radius, please note that all real systems will have the order of the denominator greater than the order of the numerator, and that is a consequence of causality. If I make a change in the input, it will take time for the output to respond, that is causality. It will never be that I change the input now and its effect happens in the past, that is simply not possible, then causality is violated, right. So, all real physical systems will have G open loop, what are we trying to say? Oh well, all real physical on the semicircle, because all real stable open loop systems have order of numerator greater than order of denominator. Basically what I will have is, if G is equal to product over I of S minus Zi divided by product over J over S minus Pi, then what I will have is, if I substitute G is equal to capital R e to the power j theta minus Zi product divided by product over j into capital R into e to the power j theta minus Pi. Please note that Z and P are much smaller than capital R. So, this will essentially boil down to the Z being negligible compared to this guy and the P being negligible compared to that guy. So, when you take the limit R tending to infinity, what you will essentially end up with is R to the power, and let us say this is I going from 1 to m and j going from 1 to n has to be greater than m because of causality, and therefore, what you will get is essentially the limit will turn out to be 1 over R to the power n minus m, n is greater than m, and therefore, this will tend to 0 for R tending to infinity. So, what that means is G on the semicircle tends to 0. Yeah. So, let us get back to this figure. So, when S equal to j omega, you get the Nyquist plot. When S equal to minus j omega, you get the Nyquist plot mirrored about the real axis, and when S equal to semicircle, so S semicircle, you get GS maps to 0. Yeah, all right. So, if I have G open loop, I can make its Nyquist plot, and as I make its Nyquist plot, 1 plus G open loop would be nothing but that Nyquist plot with the origin with 1 added to everything. On S equal to j omega, you get Nyquist plot. On S equal to GS is essentially the Nyquist plot. On S equal to minus j omega, GS is Nyquist plot mirrored about real axis, and S equal to semicircle, usually what will happen is GS maps to 0. So, you can see that for most realistic systems, just the Nyquist plot contains all the information. And now, getting back to what I am actually looking for is the encirclements, the right half plane pole, the right half plane roots of this equation. Yeah. So, if my S contour is this guy and I plot G open loop, the Nyquist plot of that guy, what I want to know is how much for each pole, for each root that is inside this contour in the S plane, what I should get is that the angle should change by, because this pole is in the numerator, the angle should change by, this is going like this. So, the angle should change by clockwise by 2 pi. So, clockwise by 2 pi is minus 2 pi. For every root of this equation in the right half plane, the angle will change by minus 2 pi. Now, if I am plotting G open loop, then 1 plus G open loop, let us say this is the Nyquist plot of G open loop. Okay. Then this is the Nyquist plot of G open loop. Okay. Then 1 plus G open loop would be what? I would simply be adding 1 to the real part. So, my everything will have 1 added, and I would just have shifted everything to like this from 0 to 1. This would be 1 plus G open loop. Yeah. So, the blue curve would be 1 plus G open loop. Okay. Now, if the blue curve is encircling, oh, what the hell, man, 1 plus G open loop would be this. Well, now if 1 plus G open loop, okay, if I redefine my axis as the blue one, where the origin is shifted to this blue curve, then if this guy is encircling the origin, that means G is sweeping an angle of, well, this is anti-clockwise, minus 2 pi. If G is sweeping an angle of minus 2 pi, that means exactly one root of 1 plus G open loop is in the right half plane, is encircled by the S contour, right. If it is encircling the origin twice, that means there are 2 poles or 2 roots of this 1 plus G open loop equation in the right half plane. So, now instead of plotting G open loop and then shifting the origin to 1 0 and calling that the new origin, what is generally done is you just plot G open loop, this is G open loop, and instead of adding 1 and shifting the origin to 0 and looking for encirclements of 0 0 in the shifted axis, in the blue axis here, this is the shifted axis, what you do is you basically plot G open loop, the Nyquist plot of G open loop, and look for encirclements of minus 1 0. These two are the same things. Okay. This is where the Nyquist plot or the Nyquist theorem comes from, and it is all about how many roots are in the right half plane. So, you take an S contour that covers the right half plane, and if 1 plus G open loop has any root which is in the right half plane or as many roots as are in the right half plane, that many number of encirclements you will get of the point minus 1 0. Yeah, because each root, this is actually a 0, I am sorry, this is actually a 0 because 1 plus G open loop has numerator. Okay. So, well, that is that. So, this is where the Nyquist theorem, where did we do the Nyquist theorem? This is where the Nyquist theorem comes from. If the Nyquist plot of G open loop does not encircle minus 1 0, well, what that means is there are no roots in the right half plane of the equation that I am looking at, which is 1 plus G open loop equal to 0. Okay. On the other hand, if the Nyquist plot encircles minus, the number of roots in the right half plane would be as many encirclements of minus 1 0 as I have. Okay. So, I hope this clarifies where does the Nyquist theorem comes from. How do we use it? Well, it is used as follows. You want, basically what we have is, if I get too close to minus 1 0, this is the G j omega, if I get too close to, and since I am okay, G open loop j omega, if I get too close to minus 1 0, if I pass through minus 1 0, I have sustained oscillations. If I encircle minus 1 0, I have instability. If I pass close to minus 1 0, I will have oscillations that die down very slowly. So, my closed loop system will keep oscillating, and those oscillations will take a long time to die down. So, what do we do to design controllers? We basically say I have to be sufficiently away from minus 1 0, so that there are not too many oscillations. Okay. So, I do not know how to show this, but yeah. So, what we do, if you look at textbooks, there is what is called gain margin and there is what is called phase margin. What is gain margin? Well, if you look at the Nyquist plot, you can see that it is quite far away from -1 0, and then what you are saying is, well, if the amplitude ratio at the frequency where the phase becomes -180 degree, this particular frequency, amplitude ratio at this particular frequency 1 by that is equal to gain margin. So, let us say I am passing through 1 by 3, then the gain margin is 3. Let us say this point is -1 by 3, then I am passing through, then my gain margin is 3. So, what we can say is gain amplitude ratio, you should design a controller. So, when I am designing a controller, typically what I will do is I will adjust the Kc. So, as I increase Kc, this curve will blow up. At higher Kc, I will get blown up curves. Yeah. So, I adjust the Kc so that my curve, for what Kc does my curve pass through -1 by 3, that is basically saying that I am designing my controller so that I get a gain margin of 3. What should my Kc be? So that my Nyquist plot passes through -1 by 3, that gives me a gain margin of 3. This is gain margin design. There is also what is called phase margin. Okay. There is also what is called phase margin. What do I do in gain margin? I look at the amplitude ratio at the frequency where the phase is -180 degrees, and I adjust my Kc so that that amplitude ratio is sufficiently smaller than 1. Okay. All right. What do I do in phase margin? In phase margin, what I do is I look at that frequency at which the angle of G open loop is equal to -180 plus phase margin. So, let us say I want a phase margin of 35 degrees or 45 degrees, then what I am looking for is what is the frequency at which the angle of G open loop, J omega of course, G open loop is phase margin of 45 degrees means -135 degrees. Okay. So, what I am now trying to do is, okay, this is the angle which is -135, and now I adjust my Kc such that at this angle the amplitude ratio is equal to 1. So, what I am trying to do is, what should the Kc be such that the amplitude ratio at the frequency where angle is -180 plus phase margin that I desire is exactly equal to 1. So, basically let us say this is -1 0. So, this is my unit circle. What I am trying to do then is, this is where the amplitude is 1. So, amplitude is 1, unit amplitude, and I have adjusted my gain such that this angle is phase margin. I just said phase margin is 45 degree. Typical rule of thumb is 45 to 60 degrees of phase margin. Typical rule of thumb for gain margin is anywhere from 2 to 4. Okay. So, Kc is adjusted so that you get a phase margin which is between 2 to 4 or a phase margin which is between 45 to 60 degrees. This is a typical design method that is recommended in textbooks. However, in chemical systems there is always a problem, and what is it that causes that problem? It is this guy called dead time. Sometimes we also get inverse response and so on and so forth. And if you have these ill behaved dynamic systems, then if you do, for example, you can get a Nyquist plot. This is -1 0, right? You can get a Nyquist plot which looks, for example, like this. I mean, you get a large phase margin. So, I do not know, something like this. So, if you look at the unit circle, this is the unit circle, this is -1 0, real axis, imaginary axis, you can see that I have sufficient phase margin, but then my curve is passing very close to minus 1 0. My Nyquist plot is passing very close to minus 1 0. So, even though I am not unstable, because my curve is passing very close to minus 1 0, I get what is called, I will get not sustained oscillations, I will get oscillations that take a very long time to die out, even though I have sufficient phase margin. You can also have other situations where the Nyquist plot is funny, and therefore, even though you have sufficient gain margin. So, for example, I got sufficient gain margin. Let us say this is what the Nyquist plot looks like. So, I have got this is minus 1 0, there is sufficient gain margin. You can see that here at this frequency the amplitude ratio is, I do not know, maybe half or maybe even less than half. However, my Nyquist plot is passing very close to minus 1 0. This one again will, even though I have sufficient, so in this case I have good phase margin, and in this case I have good gain margin, and yet when I do the closed loop, when I close the loop, I will find that these two systems are such that even though I have sufficient phase margin or gain margin, the response is very oscillatory. All right. So, clearly gain margin, phase margin is not going to work here. So, then what do we do? Then what do we do is we take recourse to what is called closed loop maximum log modulus tuning, and this is especially useful for chemical systems. And what is the basic idea? Well, the basic idea is, I will just go through the basic idea very quickly. The basic idea is straightforward, in that it is motivated from root locus, and if you look at root locus, what you will find is that well, let us see, how do I put it? Okay. Think of a real system. A real system is without any control, has a very smooth exponential response, or has a very smooth, slow, sluggish response to a change in the input. That is typical of chemical systems. Okay. Now, you got an open loop system like this. Let us say you are trying to control the output using the input. So, you put in a controller. Now, if you start cranking up the gain, and if you actually take a third order system, if you start cranking up the gain, what you will find is that initially the response remains sluggish. As you keep cranking up the gain, the closed loop response starts to show some oscillations. As you crank up the gain, those oscillations start taking a long time to die out. As you crank up the gain further, those oscillations become sustained, and as you crank up the gain further, those oscillations actually blow up. Yeah, this is what happens for most 95% of the real systems. Now, what I want is that the fact that there are oscillations tells us that there are at least two roots which are complex conjugate. Okay. Two roots of the characteristic equations 1 plus G open loop is equal to 0. Oscillations imply complex conjugate root pairs. And if you look at, well, maybe I need to cover this also. Okay, so if you have, what is the simplest transfer function that can give you oscillations? That is the second order under damped system. What is the second order under damped system? Second order under damped system is, let us say the gain is unity, it is actually tau square s square plus 2 epsilon tau s plus 1, and if you should do g j omega, you will find that this is actually 1 over tau square j square omega square, that will make it minus tau square, tau square omega square plus 2 epsilon tau omega j plus 1. And now, if you want to find out its magnitude, which is the amplitude ratio, you will find that G j omega, what would it be? Just by inspection it would be 1 over square root of real part square plus imaginary part square. So, the real part is 1 minus tau square omega square plus imaginary part square. So, imaginary part square is going to be 4 epsilon square tau square omega square, and this guy also squared. Okay. Now, if you plot this guy against omega, if you plot, for example, this is what is typically done in electrical engineering, which is called the Bode plot. Okay, so, log on base 10 of magnitude G j omega. Okay, so, if you plot this versus omega, what you will find is, if epsilon is, of course, under damped system, wait a second, where 18, 19, 20, under damped system is this guy, epsilon is less than 1, I forgot to tell you that. If you plot 20, this is called the log modulus, log on base 10 of absolute value of G j omega. This is on the y axis, and on the x axis is, well, usually it is logarithm of omega. What you will find is, as epsilon reduces, okay, let's see. Now, let me just argue it out with you. Look at this expression, look at this guy. When omega is 0, magnitude is 1. If magnitude is 1, log of 1 is 0. Okay. Now, as omega starts increasing from small values, because you are taking omega square, this omega square term will be negligible. So, if epsilon is smaller and smaller, then what will happen is, this term, the first term, it will become slightly less than 1, but however, if epsilon is tending to 0, that means epsilon is becoming smaller and smaller, then the positive term that you have will become much smaller, and because the positive term is becoming much smaller, then what you will have is essentially this term is negligible, the second term is negligible as omega is increasing slightly above 0, the second term is negligible, the first term has become less than 1. If the first term has become less than 1, 1 over square root of that will become greater than 1, and therefore, your log modulus will become slightly above 0. However, as omega is increased further, of course, this term will start to blow up, the second term will start to blow up, and then the magnitude amplitude ratio will again go down. So, you see that there is a hump that comes in the magnitude. Okay. So, what you will find is, as epsilon is going down, you get a slight hump. As epsilon goes further down towards 0, the hump becomes more prominent, much more prominent, and so on and so forth. So, the fact that you get a hump in the log modulus indicates that you got under damping or significant under damping in your transfer function. Significant oscillatoriness is indicated by this hump. Okay. This would be epsilon, okay, tending to 0. This, for example, would be epsilon tending to maybe 0.2, 0.4, 0.5, something like that. So, as epsilon decreases, that means your oscillatoriness increases, epsilon is going down in that direction. Your under damping is increasing, epsilon is tending towards 0, the hump in the log modulus curve will become larger and larger. So, what that means is, if you have a closed loop system which has a servo transfer function as G open loop over 1 plus G open loop, if you take the log modulus of this guy, which means what we are doing is closed loop log modulus is equal to 20 log on base 10 of G closed loop. If you have taken the log modulus of this guy, then if this log modulus is showing a hump, if you plot this log modulus, if this guy is showing a large hump, that means you got too much oscillatoriness. This is LCL and this is of course log omega. On the other hand, if it is showing a small hump, that means hump implies oscillatoriness is there, but since the hump is small, the under damping is not too large. So, the response is oscillatory, but not too oscillatory. So, we want a hump, but not too large a hump, and this is what is called the maximum log modulus tuning rule. So, the basic idea is hump in log modulus implies under damping and under damping is a sign of oscillatoriness. You want an under damped response, you want some oscillation, because that means the closed loop system is tuned for a fast response. But if you tune it, if the gain is too much, if you tune it too tight, then those oscillations won't die out. So, oscillatoriness is good, but too much oscillatoriness is not good. So, large hump implies too much oscillatoriness, that means you are closer to instability, too much oscillatoriness. You define G closed loop is equal to G open loop upon 1 plus G open loop, that is by the transfer function, and then you define closed loop log modulus as 20 log on base 10 of absolute value of G closed loop J omega. This is LCL. And now I revert back. If your tuning is very sluggish, you do not have a large gain, what you will find is LCL, if I am plotting LCL versus log omega, what you will find is that the LCL curve looks something like this, no hump. No hump means, well, it means there is no oscillatoriness. Okay. If you crank up the gain a little more, what you will find is the controller gain a little more, you will find that the curve moves towards the right. That means the response is becoming faster, bandwidth is increasing, response time is, closed loop response time is decreasing. If you crank up the gain further, you will find that some of the closed loop characteristic equation roots have gone conjugate, you get a pair of complex conjugate roots, and then as you are cranking up the gain further, you will start getting a hump. You crank up the gain further, well, you will get a larger hump. So, the fact that a hump is coming in LCL, that is indicating oscillatoriness, and the basic idea is if I tune such that that hump is not too large a magnitude, then what I will have is an oscillatory response with the oscillations dying down quickly. So, the response is fast and not too oscillatory. Okay. So, that is the basic idea, LCL max tuning of CISO system. Okay. Let us say it is a PI controller, let us say it is a PI controller. If it is a PI controller, what do I want? I will set, there are two unknowns, Kc and tau I. Set tau I to a reasonable value which is equal to the dominant time constant of the open loop system, or you can say you can for example get tau I from a Ziegler-Nichols type of tuning method. So, let us set tau I to a reasonable value, set tau I to a reasonable value, and then adjust Kc such that LCL max is not too large. What is the reasonable value of the about 2 decibel, and 2 decibel corresponds to a closed loop damping coefficient which is about 0.4, between 0.4 and 0.5. 0.4, 0.5 means the response is not too oscillatory, and your overshoot will also be of the order of 5%, 10%, no more than that. Okay. This is a typical way of tuning CISO controllers using LCL max tuning, where the dynamics is such that gain, the Nyquist plot is such that is not so well behaved, so that if you use gain margin, if you get a situation like this, where gain margin or phase margin, even though you have good gain margin and good phase margin, yet your response is too oscillatory. For these kind of systems, this closed loop log modulus tuning is actually a pretty good way of doing things. Okay. Now, let us say I want to tune a PID controller. What is the purpose of D action? The purpose of D action is to introduce sufficient anticipation, or as much not too much, but appropriate anticipation, so that I can crank up the Kc for the same amount of oscillatoriness. Okay. So, what do? I calculate as before, I calculate tau I, set tau I to a reasonable value. Okay. Choose different values of tau D. Let us say I choose a value of tau D which is here, calculate Kc for 2 dB, LCL max is equal to 2 dB. Okay. So, for this value of tau D and the fixed value of tau I which is reasonable, let us say I get a gain like this, Kc that I calculated for 2 dB was this. I vary the tau D to a different value, recalculate, you will find that the curve will actually look something like this. So, this is the value of tau D that allows me to maximize my Kc without too much oscillatoriness, because at each of these values of tau D I am calculating Kc so that the LCL max is 2 dB. Yeah. So, this is my appropriate value of tau D. Okay. So, this is called closed loop, maximum closed loop log modulus tuning, and you can use it for PI, PID controllers. You can also use it for P controller, there is no tau I there, just adjust Kc so that your log modulus turns out to be 2 dB, closed loop log modulus turns out to be 2 dB.